This is a video on the topic of aldehydes and ketones. And the object of this is for you to watch the video and then take the aldehydes and ketones worksheet that accompanies it and complete that as a homework assignment. So it's meant to be sort of a flipped classroom, sort of self-taught lesson. And so aldehydes and ketones, I've just shown a couple of interesting representatives of the two classes here. This is a ketone called progesterone. It is a hormone that has to do with pregnancy in females. It actually contains two ketone groups. And then this is an aldehyde called cinnamaldehyde, and it is the major flavor and aroma component of cinnamon. So how do you recognize an aldehyde or a ketone? Well, they both contain what's called a carbonyl group. We've talked a little bit about carbonyl groups before. It is a C double bonded to an oxygen, and what that leaves the carbon with is two more sort of attachment points that you can put something on. If one of those attachment points is a hydrogen and the other is an R group, then that's an aldehyde. Whereas if both of those attachments are alkyl or aryl groups, then you would have a ketone. And again, the C double bond O is called a carbonyl, and we've seen it before, and it will come up again when we start talking about carboxylic acid derivatives. So how do we depict aldehydes as skeletal structures? Any one of these, so these are four different reputations of what's called butyraldehyde, or its systematic name is butanal. But you could have three carbons depicted skeletally, and then the fourth one actually explicitly shown like this. That's a fine way to show it. I typically would draw an aldehyde like this, in which you specify that there's a hydrogen there. But you just draw that carbon skeletally. It is perfectly acceptable to do it this way since hydrogens are always implied. You could leave the hydrogen off, and that's okay. It's often also similarly just depicted in shorthand as CHO. And these are all common and acceptable ways of drawing aldehydes. I would tend personally to do either this way, showing the H, skeletal showing the H, or this CHO method. So here are some examples. This is this absolute simplest aldehyde, formaldehyde, in which you actually have a hydrogen. Both things attached to the carbon are hydrogens. That is formaldehyde. This is butanone. Its common name is methylethyl ketone. It's used as an industrial solvent. This is cyclohexanone, and I think we've shown this before in various instances as products or something, or reactants for something that we were talking about earlier in the year. This particular aldehyde is vanillin. So this is actually the flavor component of vanilla, is this benzene ring that's got an aldehyde attached to it, as well as what's called a methoxy group and a hydroxy group. How do we name them? Let's start with aldehydes. Just like other functional groups, we're going to find the longest carbon chain that contains the aldehyde carbonyl carbon. And you are going to replace the E at the end of the parent name with al. So for example, if it's 4-carbon aldehyde, butane becomes butanal. And then you're going to number the chains so that the carbonyl carbon is carbon 1. So let's take a look at some examples. So here's an example. This has 5 carbons, 1, 2, 3, 4, 5. It is, therefore, it's pentane because it's an aldehyde. Then it's called pentanal. By definition, the carbonyl carbon has to be carbon 1 because it has nothing over on this. It's going to be a terminal carbon because there's nothing on this side but a hydrogen. So all aldehydes have the carbonyl carbon at carbon 1. Here's another example. Now I'm looking for the longest carbon chain that contains the carbonyl group. There's 1, 2, 3, 4 carbons there. There's 1, 2, 3 carbons there. Here's another 4-carbon chain, 1, 2, 3, 4, but it doesn't contain the carbonyl group. So we're going to number it this way, 1, 2, 3, 4. The methyl group and the bromo group become substituents. We don't have to say 1-butanal because all aldehydes have the carbonyl carbon at carbon 1. So this is 4-bromo, 2-methyl, butanal. This particular alcohol, this particular aldehyde is called 2-phenylethanol. How does it get that name? The longest carbon chain is 2 carbons long, 1, 2. There is a phenyl group, that's what we call a benzene ring when it is a substituent. It's called phenyl. So this phenyl substituent is on carbon 2. So it is ethanol, 2 carbons, 2-carbon aldehyde, ethanol with a phenyl group on carbon 2, 2-phenylethanol. Now, naming ketones is similar but a little bit different. Again, you're looking to find the longest carbon chain that contains the ketone carbonyl carbon. You're going to replace the E at the end of the parent name with -one. So if it was 4 carbons, it would go from being butane to being butanone. Now, the difference between an aldehyde and a ketone is that by definition, the aldehyde carbonyl carbon is carbon 1. The ketone carbonyl carbon can actually never be carbon 1 because if there was a carbonyl on carbon 1, it would be an aldehyde. So you're going to number the chain so that the carbonyl carbon has the lowest possible number. So let's look at some examples. Here, it's just a straight line of 6 carbons, 1, 2, 3, 4, 5, 6. So it's hexanone. The carbonyl carbon is carbon 3, so this is 3-hexanone. So unlike an aldehyde where you don't have to say specify that carbon 1 is the aldehyde carbon, it's just implicit in the name. Here you need to do that. So you have to say 3 to make it clear that the carbonyl carbon is carbon 3. Because if I had the carbonyl there instead, that would make it 2-hexanone. Here, the longest carbon chain that contains the carbonyl function is 1, 2, 3, 4, 5. So it's pentanone. Because the carbonyl carbon is carbon 2, it is 2-pentanone. And then there are 2 methyl groups on carbon 3. So that is 3,3-dimethyl 2-pentanone. Here I've got 7 carbons, 1, 2, 3, 4, 5, 6, 7. Because the carbonyl carbon gets the lowest number if I number from this direction. If I numbered from that direction, it would make the carbonyl carbon carbon 5. If I number from this direction, it makes the carbonyl carbon carbon 3. So I'm numbering from right to left. 1, 2, 3, 4, 5, 6, 7. 7 bromo, 3 heptanone. So that's your aldehyde and ketone nomenclature. Now let's consider some reactions. I'm sorry, but before we do that, let's talk about naming cyclic ketones. There are no cyclic aldehydes, right, in which the carbonyl carbon is part of the ring, because remember, an aldehyde always has to have a hydrogen attached to the carbonyl carbon, and so that would break the ring. So the only type of cyclic, between aldehydes and ketones, the only one that can be cyclic is ketones. So by definition here, the carbonyl carbon is carbon 1. And so again, you don't have to say that. You simply call this cyclohexanone, and then you add in the substituents. 3,3-dimethyl cyclohexanone, 2-ethyl cyclopentanone. All right, let's look at reactions now. There are 2 reactions that aldehydes and ketones can undergo. Well, there are 2 reactions that aldehydes can undergo. There is 1 reaction that ketones can undergo. Both aldehydes and ketones undergo catalytic hydrogenation, so they can be reduced, and they're going to form corresponding primary or secondary alcohols. And the reagent for reducing a carbonyl group is hydrogen over platinum. You'll remember with alkenes and alkynes, it was hydrogen on palladium. For carbonyl groups, this is hydrogen on platinum. And in this case, it's simply going to be the reverse of what we learned earlier about oxidizing alcohol. If you can oxidize a secondary alcohol to a ketone, then you can reduce a ketone to a secondary alcohol. If you can oxidize a primary alcohol to an aldehyde, then you can reduce an aldehyde to a primary alcohol. So for example, if I take the compound we were naming earlier, 3,3-dimethyl cyclohexanone, and I reduce that with hydrogen and platinum. I am adding hydrogen across this double bond. One hydrogen atom to this carbon, one hydrogen atom to the oxygen. This is going to give me 3,3-dimethyl cyclohexanol. Here, if I take benzaldehyde, that's the name of this compound, and I reduce it, I'm again going to add a hydrogen to the C. So instead of being CH, it's now CH2. I'm going to add a hydrogen to the oxygen. So instead of being O, it's OH. The common name of this compound is benzyl alcohol. Its systematic name is phenylmethanol. But again, I'm reduced. So here I'm reducing ketone to a secondary alcohol. Here I'm reducing an aldehyde to a primary alcohol. I can oxidize an aldehyde. And in fact, what we learned back in the alcohols chapter was that if I oxidize an alcohol, it gets oxidized to an aldehyde, and then that aldehyde gets further oxidized to a carboxylic acid. So if I'm starting with an aldehyde, and I treat that with potassium dichromate, which we said is our oxidizing agent, that is going to give me the corresponding carboxylic acid. So this compound is 3-methylbutanal. I oxidize this with potassium dichromate, I get 3-methylbutanoic acid. Ketones cannot be oxidized. Why not? Because you have to have this H here in order to insert an oxygen to give the carboxylic acid. If there was another R group over here, then you would end up having to break a carbon-carbon bond in order to oxidize a ketone, and that does not happen with potassium dichromate. Okay, that is everything I have to say for this video. So what remains is for you to grab the worksheet associated with this video and get to it. Good luck.